Thank you very much for the nice, thank you for the introduction. And good afternoon, everyone. My name is Yoko Yamanishi. First of all, let me thank to the committee, ICRA committee members to invite me to have a precious opportunity to have a talk here. Today, I'm going to talk, the title is Emergent Functions of Electrically Induced Bubbles and Intra-cellular-CA. CA is an abbreviation of the cybernetic avatars. And today, I'm going to first to the background of the new project which my laboratory is doing. And then secondly, I'm going to talk about the research which our laboratory is doing, electrically induced bubbles and biomedical applications. Then we are back to that moonshot project, cybernetic avatar project. So actually, I self-introduction PowerPoint I just prepared, but it's my quite since several years to attend ICRA. But my background is actually fluid mechanics and thermodynamics, actually thermodynamics. And my major is going to the micro nano robot when I go back to Japan. Then I focusing on micro nano and MEMS technology to focusing on the micro scale bubbles, and then apply to the micro nano scale research. So first of all, let me introduce the Moonshot project organized by the Cabinet Office in Japan. And this Moonshot project is goal one is a realization of the society in which the human being can be free from the limitation of the body, brain, and space and time by 2050. So this is quite far away. It's a future. But we have to do to kind of the backcast way of thinking to what I have to do now to make a time to make the society realize 2050. So our research and development program with core technology is related to cyborg and avatars called cybernetic avatars, allowing expansion of human physical, cognitive, and perceptual abilities. So this project background pictures is actually in this JST website. Here is kind of the many avatars users in the left side, hand side. Here is user 1, 2, 3, 4, 5, 6, 7. And actual people is actually here user 1 or user 2 in the C side. But the actual the teleoperating of the concert, music concert or medical treatment, such a society we are targeting in 2050. So what we have to do now to make a realize for this kind of the society. Moonshot Goal 1 composed of the 7 project managers in terms of the social issues. Number 1 is increase productivity. So upper 3 project manager, social CA, social CA providing the service to individual and groups. So such as Professor Ishiguro as a project manager is cope with hospitality, moral dialogue and auditoriums. And also the Professor Minamizawa as project manager is doing the new experience sharing through the skill coalescence. And also the third project manager, Kanai, doing the operation as you wish with brain-machine interface. So in order to support such a project, social acceptability team is also existing, such as project manager Shimpo for the safe and secure, ensure the secure and safe status. And also in terms of the information technology, the engineering reliability, Professor Matsumura is doing as a project manager. So today's talk is actually new to project. Social issue is related to the improved richness of the life. So there is two teams, project managers. Professor Arai from Tokyo University as a project manager for embodied cybernetic avatar, and also my team is doing the embodied CA, especially cellular-based, very small micro-nano-based avatar. To try to embody CA to remote monitoring of living organs and intracellular. So in order to achieve these two teams, we are going to focus the two targets of this team. In the left-hand pictures is kind of the avatars in the intestines, and that is Professor Arai's team is doing. And the right-hand side is the avatars, cellular-based avatar, our team is doing. So this is remotely controlled outside of the body, and we are going to transfect some artificial material to the cell, and the cell going to be makes the avatar status, and then that cell-cell communication produce the increase the signal to export to the signal to the outside. And then that signal is going to sensing from the teleoperation from the outside. So in order to achieve that future technology society in 2050, I'm going to, our team is composed of the 6 teams. This research and development team 1 is ensuring the ethical social acceptability team, is supporting the research and development team 2 to 6. So let me explain about the research and development team of the 2 to 6 research developmental team. This 2 is the Intra-cellular-CA design and production of the cybernetic avatar, such as nanopore, nanoparticle, or the artificial gene circuit. That's a kind of the team. This team is cope with to produce the new materials to be injected to the cell. And research and development team 3 is the introduction such materials to the cell technologies team. So, for example, my case is a bubble injector to introduce that material to the cell, and also the functional nanoparticle is help to avatar to transport to the cell. And the cell-cell fusion technology also is a candidate to make the huge molecule to transfer to the cell. So based on this 2 to 3 is cooperate together to make lots of information into the cell. And research and development team 4 and 5 is in vivo and in vitro environment to evaluation of the remote control in the CA in the in vivo, in vitro environment. And the research and development team 6 is kind of the simulated environment evaluation. Anyway, so today, this is the overall of this project, but today my talk is focusing on the transfection to the large molecule to the cell. It is very difficult because a large molecule, a large information to the cell, a cell is very easy to be apoptosis or to death. So in order to increase the transfection efficiency and the cell viability is contradicting. So we need to keep it perfect to make this project active. So content of today's talk is emerging function of electrically induced bubbles. So I'm focusing on the group research and development group 3, and this is kind of my work of the bubble generation injector. So here is a kind of the several pictures to the application of using the electrically induced bubbles or plasma induced bubbles. That bubble is ejected from the glass electrode or kind of the polymer electrode. That bubble is producing at the tip of the electrode. Then so far we have done lots of wide range of the biomedical applications. So here is electrically induced bubbles. When the electric field is focusing on the tips of the dielectric material, that's is like polymers and Teflon, whatever, and that is producing some bubbles. But this is for the wet field purpose. So this kind of the bubble is existing at the tip of the probe, and then that's triggered the kind of the plasma irradiation repetitively, stably under the water condition. So using this kind of the bubble injector, we have so far done the lots of applications like enucleation on-site or the injection to the BY2 cell, plant cell, or the blood clot removal behind of the eyesight. And also the for this case is a minimally invasive pora formation. And this deposition and etching part is the powerful plasma irradiation, like toward the metal pora formation. So background of this electric bubbles, we are quickly to review the what is electric knife is. That is simply miniature size of the conventional that's surgery operational use electric knife. But in order to miniaturize of the electric knife, it's quite difficult because normally this is a medical device, so it's normally under the water condition. To electric discharge under water condition is quite a tough condition because unnecessarily electrolyte bubbles or to protein is going to stick to the knife. So in order to invent the bubble knife, we are using non-inductive resistance to reduce the output of to the bubbles, and also here is a kind of the concept view showing the glass insulated electrode. So after the several trial of the many designs of to miniaturize of the electrode, we have realized some kind of the directionally moving of these bubbles. This is directionally moving, and here is kind of the plasma irradiation at the tip of the glass electrode. And here is closed space here. That is the tips of this electric knife, and this bubbles actually is staying inside of the closed space. Then the bubble is ejected from the space. So every 30 microsec and every 2 meter per sec, this bubble is ejected directionally, same position. So it's like a rifle to the positioning accuracy of the bubble is quite good to make the pora formation to the biological tissues or oocyte. So this is a video showing the bubble ejection outside macro view of the bubble. And here is the nanoparticle, fluorescence nanoparticle is to entrained as the bubble is ejected. So this is kind of the reagent injection together with the bubble injection. So bubble is going to collapse to make the pora, and this kind of the flow is kind of help to inject the reagent. So this kind of the injector is kind of the fluid mechanics point to reach this point. So here is details of how the mechanism is. So when the bubble is ejected from the electrode, a very high speed bubble is ejected from the electrode. Then the tissue is in front of the bubbles. A bubble is going to deform due to by the high pressure, and that bubble is deformed and then makes a microjet. That microjet is here is a tiny microjet, and then that makes a pora at the tip of the. In this case is oocyte. So by using this kind of the technology, we have firstly done the enucleation of the oocyte by using this technology. And left-hand side is a conventional glass capillary enucleation, and the right-hand side is a bubble making the pora formation. And enucleation, the production rate is comparable with glass capillary, so the biological compatibility is also good. So we are going to move the story to the now. So far, we have done. I have talked about the pora formation. Now, when they are developing the pora formation, some biologists said, why don't you put the reagent together with the bubbles? So that is kind of the turning point to my research shift to the gene injection. So so far we have the competitive researcher doing the virus and riposome chemical endocytosis injection and a physical method. Our bubble injector is kind of the one of the method like electroporation or physical method like sonoporation. But our technology is because of us using the bubble, using the injection, animal cell, not only the plant cell, because of the power of to make the pora is very powerful when it's a collapse of the bubble, like such as cavitation. And also transportation technology is also quite good. Therefore, large kind of the plasmid or DNA can be transported without any damage. So this is a second point of the second design of the electrically induced bubble injector. This is a quark shell injector with red color is a reagent. So bubble is actually, reagent is coated to the bubbles, and the bubble is ejected to the atmospheric pressure. Then because of this tip is less than 50 micron, when the bubble is ejected into the atmospheric pressure, this is going to shrinks because of the Henry's law. So gas is going to be out. So it's going to be shrinked. Then the reagent itself is going to inside of the cell. So this is kind of the color high-speed camera showing the colored bubble injection under the medium condition. This blue colored bubble is flight about few hundred micron without this diminishing of the color. So this meaning of the reagent transportation is possible under the water condition. So by using this technology, we have realized to succeeded in the messenger RNA injection in xenopath oocyte, and also the fluorescence beads injection to the BY2 plant cell. So this is a particle about 2 micron is successfully without any treatment outside of the plant cell. So the story is after we are doing the success doing the gene injection, we realized what's happening. It's going to be increase the power of the bubble. Here you can see the plasma irradiation is starting through the bubbles. And then that's a meaning because it's initially started from the electric knife. Therefore, the power supply is ability to the plasma irradiation. So here is a model showing the bubble with bubble collapse and also the plasma irradiation. Because of the ambient condition is water, the plasma is quite likely to lead to the gas phase, that is the bubbles. Therefore, we not only the injection to the oocyte or brown rice such as, we are going to increase the power to make the metal ablation technology. So we called this one to the plasma cavitation technology. And if I increase the power, we realized to make the polar formation to the CFRP or kappa. The important thing is this is the ablation ability is not only the electric conductive materials, but as well as the non-electric conductive materials such as polymer can make the polar formation. So this is the mechanism of bubbles. You can see the very high-speed camera is using the microjet, and then we realized this kind of time conception, time passing through this picture. The bubble is starting at the tip of the actually dielectric material, not electrode. So that meaning is a high concentration of the electric field is key to produce the bubbles, not temperature. So after the many calculations of the FEM analysis and also the flow visualization of the plasma irradiation through the bubbles, that is a kind of propagation of the plasma irradiation through the bubbles. The bubble is first, after that the plasma starts to irradiate. So in summary, we have actually summarized the electric field and ambient conductivity is very important. And discrimination between two phases, actually when the vaporization of the, after the vaporization of the water, when it's breakdown, without breakdown of the plasma irradiation, the gas of the bubble is H2O. And if it is a breakdown, the gas of the in the bubble is kind of the electrolyte component of the reagent. So this kind of they switch to these two by controlling the breakdown. So by using the physical effect, we are, I'm talking about the polar formation, but here is a chemical effect when the plasma irradiation. So air-water interface here is kind of the reducing effect is produced. So this is a kind of the model is showing of the bubble and the plasma irradiation, and the air-liquid interface here is a hydroxy radical is existing to reducing the metal ion liquid. So that leads you to the kind of the electroplating, instantaneous electroplating at the water content substrate, such as the plastic or biological tissues. So here is kind of the electric stain of the chicken meat, and the CuSO4 is actually doing the deposition. And also the deposition to the circuit at the rubber glove, and you can see the LED light is on by using etching the deposition simultaneously to make the electrical circuit. So we are back to the video, which is showing that the first plasma irradiation stably, repetitively controlling of the bubble is actually finally to do the stable deposition. This is a filming from the backside of the substrate of the glass, and you can see the kappa is deposition on the glass, and then that's actually makes a circuit to make the LED right on. So this technology's advantage is we can do some deposition on the wet substrate, such as biological tissues. So that's meaning is leads you to the future is like this is electric circuit on the body. So emerging function of the bubble injector is, first we have started from the polar formation, but now is going to the kind of the adsorption force of the air-liquid interface and reactivity. So by using this technology, there is many crystallization. Today, due to the limitation of the time, I didn't have time to talk to. But the last 5 minutes, I'm going to talk about large molecule injection by using this technology. Electromechanical poration for large molecule transfection. So we are going to back to the first topic, moonshot project. We need to inject a large molecule to the cell. In order to do that, 10 to 7 or 10 to power 8 molecule weight or 10 to 6 base pair, such a large, for example, gene is fragile and easily to be break down to the shock of the physical stimulation. So in order to protect such a large-scale gene or artificial material to put transfection to the cell, we need some kind of package protect and make open and load and unload. So our different project is doing some using the DNA nanocrystal to protect the gene, to protect the gene and then injection with this crystal. So by developing of this bubble injection toward the this kind of the large molecule injection, during we are developing the technology, we realized it's impossible to make the polar formation direction. But because tissues, not tissues, biological cell is quite a number of the cell is existing. We need to high throughput injection and minimally invasive. So here is a low concentration the cell is the method of the which I'm going to explain so far. And here is a high concentration bubbles. It looks like a cyclic bubble oscillation to make the stimulation, the physical stimulation ambient region. So by using this technology, actually we realized if the increase the density of the cell, so increase the transfection efficiency remarkably as in terms of 3T3 cell and osteoblast-like cell. So why this is happening? And also the larger scale gene is also it's successfully to be injected. And we realized it's kind of the massaging of the cell is a stimulation of the electric, the mechanical oscillation toward the ambient stimulation is good for probably the injection. So to prove what is happening in the cell, we checked the disruption of membrane acting cortex by using the pharogen reagent to show left-hand side is a low concentration of the cell, and the right-hand side is a high concentration of the cell. Here, it is something happening in the actin fibers, and then after 24 hours, this actin cortex is appeared again. So I think the this kind of the physical properties change is kind of the effect to increase the transfection efficiency of the cell. So by using the by achieving the this physical property without increase the density of the cell, we just simply put the thickener, and then UMR 106 and chlamydomonas MSC cell all increase. We realized the increased transfection of the efficiency. So this is the front cover of the lab chip last year. It's kind of the physical stimulation, cyclic stimulation to increase the large molecule of the cell. So the last pictures is here is the red color is the kind of the crystal, DNA crystal. The size is nearly 1 micron. That's successfully to be injected in the UMR osteoblast-like cell. So we realized last 30 seconds, I'm sorry, is the, okay, so maybe possible to large molecule to be injected, a transfectant to be introduced the cell. So that is connecting to the creating the moonshot project. So this is the today's talk, and this moonshot project is based on the first is a Fantastic Voyage, that is a long time film. At that time, the human itself is going to be smaller, get that purpose to be achieved. But our project is focusing on to make the cell itself is to make the cell is reflect our will, the cell itself moving to make the treatment of the cell in the body. So this is a need to the many collaboration is necessary: engineering, science, chemistry, information technology, genetics, biology. Many scientists is collaborating with this project. So we are treatment with kind of the many, it's now making the artificial material to be injected. Injection material is our technology, and that is going to make the cell to be avatars. And that avatar cell-cell communication is produced, then the information is going to expand to the outside of the body, and that is going to be keep the human healthy condition in 2050. So here is one example of the cell-cell designed cell-cell communication, and that signal is going to pass to the another cell. So the collaborators is very young, actually. I'm oldest of this team, and that's all the team is all different field. So interdisciplinary, the major is going to be merged and then produced one good target to the 2050 goal. So I'm going to talk very fast. I'm so sorry about that. So we are actually targeting, our project is just started for the avatar cell. That is based on the technology that the large molecule is successfully to be injected to the cell. So thank you very much for your attention. So this is the end of my talk. Thank you.